So we're going to see examples, okay? Let's start talking about examples. So this is the same robot as the one I presented in the beginning. I hope you don't need any more explanations on this, but let's try to see what are the Denavit Hartenberg parameters and how do we define the direct geometric model of this robot. So I start by drawing the coordinate frame, the fixed coordinate frame. And I have the first joint here that rotates around the z-axis of the fixed frame. Okay, then it goes up. Let me make it more thick. Okay, then here I have another joint. Okay. Here I have another joint. And this joint. And then another one here. It's slightly different than the one we saw in the beginning, but same idea. So first joint along this direction, Q1. Second joint in this direction, Q2. Third joint horizontal, Q3, 3, and Q4 again along this direction. So I have my fixed frame and I want to find out what's the direct geometric model of this using the Denavit Hartenberg convention. Okay? Step 1. What was step 1? Put a z-axis for each joint. How many joints I have? 1, 2, 3, 4, right? So I need 4 axes. How do we choose where to put the axis? Z1 should be aligned with the axis of rotation of joint 1, and this is horizontal, vertical, sorry, right? So this will be my Z1 all the way to infinity. Don't forget that, ever. Should it point up or down? Doesn't matter, you choose. Let's say it points up. And I make it so big so it is clear that it goes to infinity. You'll see why. Okay, so Z1 in this direction, pointing upwards, positive. Z2, diagonal, so pointing towards you or pointing inside, right? So along perpendicular to the board, right? Pointing towards you or inside? Inside? Oh, yeah. More difficult to do. And this is Z2, Z3, joint 3. What is the axis of rotation? Horizontal. So this way, I put it towards the right. I wrote it now. But you could have put it towards the left, doesn't matter. And Z4, this one, right? Along this direction, let's put it pointing towards you. Okay, so this points towards you. Okay, and we define also a coordinate frame at the end effector, as I said earlier to one question. I'll define one coordinate frame. I can define however I like it here. Z, X, let's say. And this is Z5, X5. Okay? Same robot. Lengths I don't add, but we'll see how they affect. Next step. So I identify Z's with the axis. Identify the x-axis. How do we identify it? The common perpendicular between subsequent axes. Okay. One small detail is that this is not x and z, this is x0 and z0. Okay. So what are my first axes? Yes, z0 and z1. Yes. Okay, so I need the common perpendicular between z0 and z1. What is that? We choose whatever, okay? Not whatever, almost. It has to be perpendicular to these two lines. But it can be any vector pointing in this direction, and it can be on any height, right? Let's say we put it down here. And let's say it points the same direction as x0. Yes. Okay, next one. So wait a bit, sorry. I made a mistake. Because that's why it doesn't make sense. We said that xi is the common perpendicular between zi and zi plus 1. So my mistake is that I defined x0 basically. That's where it started from. Because I shouldn't have defined x0 on my fixed frame, because the x0 is defined according to this rule as well. I defined just z0. Okay, my mistake, sorry. And you see that this brought me to confuse myself. So z0, when I is 0, is the perpendicular, no, sorry, x0, when I is 0, is the perpendicular between z0 and z1. Right? So this is I choose as my x0. My x1 is perpendicular to z1 and z2. Right? Don't get confused like me. So, what is the common perpendicular between z1 and z2? z1 is this one, and z2 is pointing inside. So it's basically this and this. Huh? Say again? On z1, like here. But it has to be perpendicular to this and to this. Right? If it points like this, it's not perpendicular, it's parallel. This hand? This hand. It's pointing towards there, basically. Right? So if this is z1, z2, this is x1 or 2? x1. Great. So now, when we say common perpendicular, it has to be perpendicular to both, and to be perpendicular, it needs to touch it. It needs to intersect it. Okay? So yeah, it has to point towards there, but it cannot be here, because this is perpendicular to z1, but it's not perpendicular to z2. So z2 is up here, and this is down here. They have to be at the same level. They have to intersect. Okay, so z1, x1, is up here. Okay, at the intersection of the two. I didn't draw it exactly there, so it's a bit more clear. Okay? That's a common mistake many students do. Being perpendicular means they intersect. So even if you would think that x1 should be here, because here is the joint, no, it's up there. Good. So we define x1, what do we do next? we define x2. How do we define x2? Z2 and so x2 is perpendicular to Z2 and Z3. Okay, Z2 it points in the board, Z3 points, so Z2, Z3, Z4, X2 or X2 out. Okay, so basically it points here, yeah, it's gonna be pointing upwards or downwards. Upwards or downwards? Why? The positive xi from zi to zi plus 1. That's the convention. But then zi plus 1, they are together. They don't have a distance to have like zi. So then we can put it wherever we want. Doesn't matter. Okay? Up or down? Up. More ups than downs. Do you know the game? One up, one down. We play it one day. X2. So X2 is perpendicular to Z2 pointing in and Z3. Okay? And if I put it here, it intersects with Z3 and Z2. So it's okay. Next, X3 is perpendicular to Z3, Z4, pointing upwards. Same thing. The X3. Okay. X4 perpendicular to Z4 and Z5. Z4 and Z5. It's going to be a line like my hand, right? Here. Here it makes sense to use this last rule. Positive is from X3, from Z3 to from Z4 to Z5. Right? I could put it inverse, it's not a big problem, but we usually prefer this. Okay? If you do this right, then you're halfway only. If you do this wrong, then everything else will be wrong. So pay a lot of attention how you define the x-axis. The z-axis is easy, although I've seen weird stuff there as well. But the x-axis, be careful how you define it and make sure that it's perpendicular to both z's. Good. Let's define all the parameters now. So, the question, you have any question? No, okay. So, what we said is that we need 4 parameters for each theta and alpha, and we need 4 parameters for each link, so every pair of joints. So from 0 to 1, let's call this I. This is from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5. Okay? This is the I, Ri. And let's figure out what are the parameters. So basically this table is what I need. And then I know the direct geometric of the robot, the direct geometric model of the robot. Okay? Let's see. Let's start with R, from 0 to 1. What is R0? The distance between Z0 and Z1. It's basically, they are parallel collinear, so it's 0, right? One is on top of the other. Good. What was alpha? Do you remember? Great. So zi plus 1 along xi, so along this angle basically. Okay, xi points towards there, so it's this angle here. But they are parallel, so the angle is 0. What was D? Very good. Do you have notes? Then you have a good memory. So the distance between x0 and x1 along which axis? z1. z1 is this, so it's basically this distance here. Okay? Which was L1 on the drawing. Let's say L1. And finally, theta was the angle between x0 and x1 measured around z1. If you see, it follows like a pattern. zi plus 1, xi, the distance and the angle. And then the distance and the angle, xi plus 1, zi plus 1. So what is this angle between x0 and x1 around zi plus 1? So it's basically this angle. So around zi plus 1, so around z1, x0, which is here, let's say this is x0 and x1. Right? Is it 0? It's not 0. Why? Why is it Q1? Basically, I have a robot, and if it was 0, then I would not have any transformation. It would be a fixed transformation from here to here. Okay? It kind of makes sense. There is some variable there. Now, why is it Q1? We said that Q1 is this rotation here, right? Around this axis. Is x1 and x0 and x1 changing orientation though with Q1? Yes, they do. Why? Now that requires a bit of imagination. Now imagine this robot was not like this, but it was like this. Okay, pointing towards you. Right? How did we define x1? Is the common perpendicular between, let's see. So xi is common perpendicular between zi and zi plus 1. So x1 is common perpendicular between z1 and z2. Okay. z2 we said points towards the screen. Right? Because it's this rotation. Okay. But if I move with Q1, then Z2, let's say I move by 90 degrees, Z2 will stop pointing towards the inside the screen and will start pointing towards my left, towards your right, right? Because Q1 changes the orientation of Q2. Right? Do you visualize it? Should I move more? Okay. If Z1 did not change orientation though. Z1 remains the same because I rotate around Z1. Okay. Z2 changes orientation. Okay. If x1 is perpendicular with Z1 that doesn't change and Z2 that does change, then x2 will also change. So if this is x2, when Z2 is pointing there, in order to remain perpendicular to Z1 and Z2, it has to rotate as well. Right? How much? By Q1. Okay. So the angle between x0 and x1, x0 being a fixed one on the floor and x1 being my right hand, is variable. And it's exactly variable as much as the joint moves. Okay? That's why my theta is equal to Q1. Clear? More or less? More or less. It doesn't have to be super clear. It takes a bit of... You will sleep on it, wake up, go have some beers. During the beers, you will go, oh, now I get it. Then you'll forget it, then you'll remember again. Okay. So that's how we define the things. You see that this distance here is actually a length, and this angle here is actually an angle. Okay, so things make sense. Make sure you double check this. Don't put me here like an angle 30 degrees or 90 degrees or something, because these are distances, these are angles. Okay? That's also like a sanity check to realize if things are going fine or not. Good, so we finished with the first joint after 20 minutes. It's gonna go faster. Let's go with the second joint. Okay, so I equals to 1, talking about from 1 to 2, right? Let's see. Ri is the distance between Z1 and Z2. Z1 points there, Z2 points there. They're basically intersecting. So the distance is 0. R. Okay? Alpha. The angle between Z1 and Z2, pointing there, Z1, Z2, along which axis? X1, X1 pointing there, right? And you remember that X1 changes orientation with Q1, but so does Z2, so it will always be, pointing in front of me, right? So what is this angle? From Z1 to Z2, along this vector. Positive direction towards you. Positive or negative? Why? Because if I use the right hand and I do this rotation, my thumb shows the negative direction. Okay, so this is minus 90 degrees. Okay? Sometimes when I try pi over 2. Great. Next, delta d was the distance from x1 points in front, x2 points upwards, but they're both at this position, so they're intersecting, so it's 0. And theta was the angle between along Z2. So x1, x2 along Z2. x1 points there, x2 points there, and Z2 points inside. So it's basically this angle here. How much is it? Is it fixed? Because here you have to think a bit in pattern. Is it Q2? Why is it Q2? Is the angle here changing? Okay, so now I forget what happens behind me, because I just care about this link. So what happens from 1 to 2? So whatever happens behind me does not affect me. I'm fixed. I'm sitting on this joint here, and I move together with it. Basically my Q1. Okay, so whatever happens behind it does not affect me. Okay? Does the orientation between x1 and x2 change, the angle between them, with Q2, and why? Doesn't change. Okay, so how did we define x2? x2 is common perpendicular between Z2 and Z3. Right? So if I rotate around Z2, Z2 is not changing, right? I just do this. But the orientation of Z3, is it changing relative to x1? x1 is perpendicular to z2 and z1, okay, and that does not change after z1, okay, but the orientation of z3 is changing because I rotate around z2 by q2, okay, so I do this thing, and as I do this thing, my x2, which points upwards, is also changing, okay. Therefore, this angle is also variable. Now, I can say that this is 90 plus Q2, or I can just ignore this offset, this 90, and I say it's Q2. Okay? If you write Q2 plus 90, I'll take it as correct. No, I will not take it correct because it should be Q2 minus 90, because x1 to x2 is a negative rotation, because x2 points there. Anyway, but the idea is that, okay, I can introduce an offset there and say Q2 90, which means that when I consider my Q2 to be 0, I consider these two to be perpendicular, so I consider my neutral position of the robot this one, and not when the robot is pointing downwards, when x2 and x1, but that's a detail. Okay, the point is to understand why here I have a variable. Okay, because my x2 is changing orientation relative to x1 when I'm moving this joint, q2. Okay? It's the same reason why x1 is changing orientation with x0 together with q1. Okay? Good. Third joint. Let's start the inverse. What should be theta 3, theta 2? So theta 2 should be x2 and x3 around z3. So x2 and x3 around z3. So x2 points up, x3 points up, and I care about this rotation here. I don't know how to do it. This one. Around this axis. Okay? Basically, if I explain again the same things, this one is perpendicular to Z4 and Z3. Z4 changes orientation with when this rotates, so X3 also changes orientation, and here we're going to have Q3. The idea is, when I have a revolute joint, my theta will always be related to a Q. Always. Okay, so you get one parameter for free. Okay? That's how the convention is defined. That will always give me theta equals to Q3 if I have a revolute joint. Okay? If I have a prismatic joint, it's a bit different. So if and then I say here, if I plus 1 is a revolute joint, so if Q3, so I am at I2 here, okay? If joint 3 is a revolute joint, then theta I, so I equals to 2, will be a variable that relates to joint variable Q I plus 1, so Q3. Okay, to the next one. Okay. Now quickly, how about delta rho and alpha? What should be R? R is the distance between R2, okay, Z2 and Z3. Z2 points towards there, Z3 points towards there. They are intersecting, so they're 0 distance. What is the angle between Z, so alpha Z2, Z3 along X2? X2 is pointing upwards, Z2 inside, Z3 there. So this angle and x2 is pointing upwards. My thumb points downwards. Okay, this means that it's a negative degree. That's why it's very important to know around which axis are we measuring. Okay, minus 90. And the distance between x2 and x3 is L2. Okay. Now, this one, what will this one be? It's basically the angle between x3 and x4. And this one is an angle like this. It's equal to Q4. No questions. I don't even think about it. Just make sure it's a revolute joint. Okay. Then alpha, the angle between Z3 and Z4 around x3. So this angle, minus 90 again. Ri, the distance between Z3 and Z4 is also 0. And the distance between x3 and x4, 0. Good. Next one. What should I put here? Why? Why not Q5? You're too clever. Okay. We don't have a joint there. Yeah. Why 0? Because I define x4 to be perpendicular to Z4 and Z5, and x5 to kind of continue there. So it's by my definition that it's 0. Okay. The angle between Z4 and Z5 around x4. So Z4, Z5, x4. This angle, minus 90. The distance between Z4 and Z5 along x4 is this length here, L3. And the distance between x4 and x5 around Z5, if we consider this to be a line, it's 0. Now, this is the solution I have on the slide, so you can see it. Why is this not the same as this? Besides the difference in the columns. For some Z, for some X maybe. Yeah, you see for me Z2 is pointing outwards. You point it inwards. Okay. And I think that's the main difference. Yeah, that's the only difference. Okay. Will we get different results? How come? Yeah, basically it's like going from here there. I can have different ways of reaching the same place, right? It's just that, yeah, I define some axes differently, therefore some rotations are negative, while for the slides is positive and things like this. But overall, if I use these parameters or these parameters, I should get the same direct geometric model. Otherwise, I made a mistake somewhere. Okay? Now, how do I get a direct geometric model from this? We write the transformation. So I write this thing, or basically this thing, for each row. Okay? I calculate the transformation from 0 to 1, from 1 to 2, from 2 to 3, and so on. I combine them together, and I get my overall transformation matrix from fixed frame until the end effector. Okay? Questions? Do you want to see another example? Basically, I said that here my Q will be my theta will always be Q for a revolute joint. What do you expect to be the case for when I have a prismatic joint? Like in this case. The R is Q3. Okay, your intuition is correct because I have a prismatic joint and my variable is a distance now, it's not an angle. So it should be one of these two being different. It's actually D, that is Q3, Q4, or whatever, Q3. Yes, I didn't forget. Why? Let's take just the joint before. Okay, and the joint afterwards. Let's say here as well. Okay. It's visible? Is it visible? Yeah. Okay. So this would be my Z. Now, when I have revolute joints, I said that I align the Z along the axis of rotation. When I have prismatic joints, I put the Z along the axis of translation. Okay? So I will put the Z here, and another Z here. Maybe that's actually a weird example. Okay. So my X, so this is, let's say, 1, 2, 3. My X1 will be perpendicular to this and this, so out and left, so let's say up. X1. I chose like around, this is not going to give us very clear results. Let's say I have a joint again like this. Okay, sorry for the confusion. So this is my Z3. Okay, so X1 is perpendicular to Z1 and Z2. X2 will be perpendicular to Z2 and Z3, right? So here. And Z3, we don't care. Okay, so what did we say are the 4 parameters? R is the distance between Z1 and Z2 along X1, which is 0. Anyway, it's fixed in this case, right? R will be 0, while delta D is the distance between Xi and Xi plus 1, so X1 and X2. Okay, and this distance depends on this variable here, how much it's like. Right? So this is going to be Q3 or whatever. Okay? So when we have revolute joints, theta will be the variable of the joint, of the next joint. When I have prismatic, D will be the variable of the joint. Now I have 4 examples in the slides. I recommend you go through them. Okay, I have like a slide, just the robot, and a slide with a solution. Just the robot solution, just the robot solution, just the robot solution. Okay? What do you see here, just so you understand if you go home and you study? I have the red is the fixed frame, sorry, and I use colors. So light blue is the first, green is the second, third is the purple, orange, blue is the fourth one, and the fifth one. And here you see from 0 to 1, from 1 to 2, from 2 to 3, and what are the parameters. Okay? And you can see how I put the axis. So I recommend that you take this and you draw the axis yourself, then you verify what are the axes. And you try to understand if you made a mistake, or you can also talk about it next time, or mail me, or in the labs, or something like this. Okay? And after you make sure that the axes are correct, then calculate the parameters as well. Try to do it. I think it's a fun activity, and yeah, depends how you define fun. But yeah, this is a probable topic for exams, let's say, if that matters anyway. Yeah, you will get to practice in the labs. Like at every lab, you will derive the Denavit Hartenberg parameters, the next 3 labs. So you will get practice. And yeah, this is the explanation for the revolute and prismatic joints, what parameters is what. Okay. Now, to confuse things even more, there are 5 more slides. There is another way to define the parameters. There are 2 different ways of defining the same thing, kind of. It's like, I don't know, some people prefer this way, some people prefer the other way. I prefer this way. There is another way, an alternative form. It's very, very similar, but instead of defining, let's say, instead of defining x as common perpendicular between zi and zi plus 1, you define the zi and zi minus 1, and some things are slightly different. I have it there as well, just to confuse you more. And the way that these are defined is also different, but the concept is the same thing. I'm just having it there not to confuse you, I'm kidding. It's there just in case you open another book and you see, oh, this is totally different. What are we learning here? You know? I'm not lying. It's just that it's 2 different methods of deriving the same thing. In some books it's this way, in some books it's the other way. Okay? Questions? No?